Hello, in this video I'm going to solve the question from chapter Eigenvalues, Eigenvectors. The question will be about diagonalization of matrix. First of all, let me indicate what is eigenvalue and eigenvector, and also we have one more uh, academic word as characteristic equation. So eigenvalue is will be lambda. What about characteristic equation? It is determinant of A minus lambda multiplied by identity matrix, and which is equals to 0. Uh, you have to find the matrix P, which is about eigenvectors, and also you have to find um, D. It's diagonal matrix where entries are going to be our eigenvalues, which is lambdas. So let's go to our question. So we have matrices such as mm, 2, 1, 0, 0, 3, 0, and minus 2, 2, 3. First of all, let's apply the characteristic equation. Lambda 1, 0, 1. This matrix is identity matrix because on the main diagonal we have only ones. So we will have 2 minus lambda, 0 minus 2, 1, 3 minus lambda, 2, and 0, 0, 3 minus lambda. Let's apply determinant for our matrix. So as you know, we can find the position that has on the same row or on the same column a lot of zeros. In this case, we have the last row and the last column. The intersection is going to be in this position. So let's move on. It's going to be 3 minus lambda, which is coefficient, multiplied by minus 1. The position of this coefficient is in the third row and in the third column, and the determinant 2 minus lambda, 0, 1, 3 minus lambda. That is 2 minus lambda multiplied by 3 minus lambda minus 0. So we'll get 2 minus lambda, 3 minus lambda squared equals to 0. So from here, lambda 1 is going to be 2, and from this brackets it's going to be lambda 2 equals to lambda 3 equals to 2 because we got 3 twice, 2 times. So let's write one more information like multiplicity 2. Step number 2, we will work with our eigenvalues and to find the eigenvectors. So lambda 1 equals to 2, and you have to write again our characteristic equation, but no, not without. You have to write without determinant. It will be a kind of linear combination. We can consider this brackets as just one matrix, which is B. So let's write it immediately. So since it's matrix A minus lambda I, but we already have our lambda, which is 2. We can just put instead of lambda 2, so it's going to be 0, 0, minus 2, 1, 1, 2, 0, 0, 1. Since we have a linear combination formula where B vector is 0, so we have to write this matrix in terms of homogeneous matrix. 0, 0, minus 2, 0, 1, 1, 2, 0, and 0, 0, 1, 1, I, 0. Let's interchange the rows 1 and row 2. We got pivot position in the first row and in the third row. Variables x1 and x3 are going to be our basic variables. x2 is free variable. So x3 equals to 0 from the third row, from the second row as well. So, but from the first row, x1 plus x2 plus 2x3 equals to 0. We can eliminate this, so it's going to be x1 equals to minus x2. So let's write our x vector. That is minus x2, x2, and 0. In vector form is going to be x2 with entries minus 1, 1, and 0. So it's going to be our first eigenvector, v1. For lambda 2, lambda 3 equals to 0, I3. So it's going to be minus 1, 0, minus 2. 1, 0, 2. 0, 0, 0. Let's write homogeneous matrix. For operation, R2 is R2 plus R1. 0, 0, 0. We got pivot position only in the first row, first column. Minus x1 minus 2x3 equals to 0. So x1 is going to be minus 2x3. Minus 2x3, x2, free variable, and x3 is also free variable. So let's write our vector equation with two unknown variables. 0, 1, 0 plus x3 is minus 2, 0, 1. It's our second eigenvector and it is our third eigenvector. Let's prove them that those eigenvectors are linearly dependent. What we are going to do now, we are just going to include those eigenvectors in one matrix to prove them. How we can prove them or how we can define them, we have to do row operations to get pivot position in every column. So R2 is R2 plus R1, 0, 1, 2. No, no, no. It's minus 2. 0, minus 2. 0, 0, 1. So yeah, we got pivot position in every column, so we can say that it is linearly independent. So we also can confidently say that A is diagonalizable because we have three linearly dependent eigenvectors. So what about D and P matrices? D is diagonal, which consists diagonal with eigenvalues such as what was that, 2, 3, 3. Other entries are zeros. What about P is our eigenvectors, which is v1, v2, v3, and let's write it again. Minus 1, 1, 0, 0, 1, 0, minus 2, 0, 1. That's it. Thank you for your attention.